So Unit 2 review. Again, this is on probability. Okay. So in the textbook, it was chapter 13 on probability. All right, and again, we're looking at the problems that I asked y'all to do, number 1 through 39. So if you look at the first one, this is a coin is tossed, a die is rolled, and a card is drawn from a deck. How many possible outcomes does this experiment have? Okay.
All of those?
Yeah, how would I find out how many possible outcomes this experiment have?
A coin would be 1 out of 2.
Okay. But I'm not doing probability on this. We're counting. Okay.
Yeah, that would be 2.
So you got 2 options on the coin
Next
toss.
one would be 6. Die 6.
A die is 6 options.
And a card's, is it 52 or 42?
52.
52, so die.
So you got 52 there. And what's true about all these events? Are they independent of each other? All right.
So it would be 2, 6, and 52, which would be 60.
And what am I going to do with these 3 numbers?
Add them.
We're actually multiplying. So if I multiply all these together, 624. Okay? And that's what you get. Okay? You do have to be aware, guys, when you're doing the calculation. Am I finding probability or am I counting possibilities? Okay? So if you're counting, you're going to use your fundamental counting principle, which is what we're doing here. Another way to do this, guys, would be to do a what diagram? Like a tree diagram kind of thing?
Pattern, kind of like pattern.
Yeah, but I'd start out with 2 options and that goes to 600. You don't want to do that.
This was like.
That'd be a pain. Okay? With 52 cards, by the time you got to the end, the test would be over. Okay? So again, you got to know the simple way. All right? Number 2 says how many 3-digit numbers can be formed using the digits 1, 2, 3, 4, 5, and 6 if repetition of digits A is allowed.
What does that mean? Like numbers? Does it mean like you take 2 and 1 and make 12? Or does that mean like you add them up and that's like you did? Which one just multiply? What? What's that one asking?
Can you repeat that question?
Like, what's the question asking? Like what? You put them together? Like.
Yeah, like 345 would be 345. That's what's asking.
Yeah. But you gotta count up how many possibilities are there.
On the calculator for all combinations.
It could be a combination. Okay. And you're doing 3-digit numbers, right?
We don't have a calculator.
Oh, and we weren't even doing this one, but let's go on and do it. Okay.
We don't have a calculator. What's the combination problem?
I know, but it's okay. You can use today your cell phone if you wanna.
You do combination
Calculate.
also?
I don't know. Am I going to use a combination on this?
You can. This order doesn't matter.
I think we can just use the fundamental counting principle. Okay?
You could do that too.
If repetition is allowed, I'm doing a 3-digit number. I have the digits 1 through 6 I can use in the first space. So that's 6 possibilities.
Repetition, you could put 111, right?
Can I repeat a number?
That's what it says, repetition.
So I can use 6 digits on the next, 6 digits on the next, and then what's 6 times 6 times 6?
6 times 6 to the third, basically.
6 to the third, which is what?
216. Something like that.
I don't know. Can y'all do it? I don't know.
That's 216.
Yeah, 216. All right. And guys, the only thing that changes on Part B is we don't allow repetition. So if I use one of the digits on the first number or first digit, then I only have 5 choices on the next, and I have 4 choices on the last digit.
So it would be actually.
So what's 6 times 5 times 4?
30 times 4 would be 120, right?
Yep. So 120. All right. And then you're done. All right, number 3. All right. 3 says, how many different 2-element subsets does the set A, E, I, O, U have? Okay.
What's it mean 2 subsets? What's that?
Like if I took 2 of those at a time, like A and E, O and U.
Okay, and they're, I guess. So you could do A, E, and then E.
Well, it says a subset. Does the order matter in subset?
Nope.
Would A and E be the same as E and A?
Yeah.
Yeah, so I don't use a permutation there. I use a combination. And all you do is say a combination. And how many objects do I have?
Yeah. 5.
5 that I'm choosing from. And how many am I taking at a time?
2.
2. So if you do the 5 choose 2 or 5 combination 2, 5C2, however you want to read that, then there are 10 possibilities. Okay? Do you guys remember how to do that on the calculator?
Yes.
Because again, I don't have the calculator.
It's like math something.
Yeah, it's math. That's the first button. And then I think we do the back arrow to take us to probability, PRB.
What do you mean back arrow?
This back arrow. Right here, that back arrow.
Left arrow.
Yeah, so I'm going to do math, back arrow, and see the NCR right there is 3.
Yeah, I've never known.
So it's option 3. Now guys, the first thing I have to type in though is that 5. So I'm doing 5, math, back arrow 3, and then I put in my 2, and then I hit enter. Okay? So that's what you're actually typing on the calculator. So we're going to do that here. We're going to say 5, math, back arrow, 3, 2, and that's 5 NCR 2, and hit enter, and you get 10, okay, which is what we got there. So again, you have to remember your calculator keystrokes, because if you don't, I hope you know the formula, okay, because that's your only other option is to do the formula. And we're looking at, that's number A. Part B of number 3 says how many different 2-letter words can be made using the letters from the set in part A.
So that means 0.
Well, that's different because now order matters.
You guys have a word.
Because
Any words that was.
Okay. It doesn't have to be a real word. That's why words is in quotes. They're saying words as in different formations of the letters. Like A.
So instead of doing a combination here, if order matters, it's the same thing.
5 permutation 2 is equal to 20. Okay?
And then you're done with that. Okay? And again, it's the same calculator keystrokes, except for option 3, you're not going to choose that one, you're going to choose option 2, because 2 is your NPR. Okay? And no, that's not National Public Radio. Yeah. I'm glad I'm not a vase because I cracked myself up. Alright, a quiz has 10 true-false questions. How many different ways is it possible to earn a score of exactly 70% on this quiz?
Order doesn't matter, so it would be a combination of them.
Yes, combination. Order does not matter because it doesn't matter if I got question 2, 5, and 8. That's the same as question 8, 5, and 2.
So wouldn't it be 7 combination 10?
Yeah, combination, but how many's on the
10?
10 questions,
Seven.
and then 7 at a time, and you end up with what? It's going to be 120. Okay, and again, same calculator keystrokes as we had up here, except you're going to type 10, math, back arrow 3, 7, enter, and get 120. Okay? So again, you have to be able to decide, am I doing a combination or a permutation, and then know how to find it on the calculator. Okay? But again, if order doesn't matter, it's just the same group. Like that whole table back there, if I rearrange you guys, you're still the same set of 4 people. That's a combination. Okay?
Can we go to some of that probability, like the games and stuff?
Yeah, we are. We're getting there. What's next? 7. So number 7, if I scroll down here, it says, if you must answer let's use the scroll bar there. If you must answer only 8 of 10 questions on the test, how many ways do you have of choosing the questions you will omit?
10 combination too, right?
Okay, 10 combination.
You only have, is this?
Yeah, 10 questions, so there's 2. And that's equal to what? That's going to be 45. All right. So you're doing 10 combination 2. And I always read it combination of 10 items taken 2 at a time.
We got calculators back tomorrow for the test.
Yes, you will. Yeah, they'll be back probably by the end of the day. So, and I'll have them ready for you. All right, number 9. Okay. Number 9 says a company uses a different 3-letter security code for each of its employees. What is the maximum number of codes a security system can generate?
No, it doesn't say how many employees we have. Board doesn't matter, bro. It doesn't say how many employees they have.
Yeah, but you're trying to find out the number of employees possible. So how many different codes are possible because they're unique to each employee?
You got, it would be 3 combinations.
But these are letters, right?
3 combination at 26. No,
Mm,
or 26. I'm not gonna use 26.
no.
3 letters.
See, the thing is, guys, it's harder when you have problems all mixed together because you want it to be a certain way. Because you guys are looking at doing combination and permutation right now, but you're forgetting what we just did a while ago. Okay? Each letter choice in the 3-letter code is independent of the other. Okay? So all I have to do is treat this as a fundamental counting principle, just like we did the license plates. Remember, we did the same problem and said how many total license plates are possible. Okay? This is the same problem. But I have a 3-letter security code. So all I'm going to do is say I have 26 letters in the alphabet. It doesn't tell me that I can't repeat a letter. So I can do AAA.
So you do 26
Okay.
times 3? 26 times 3?
Not times 3.
26 to
26 cubed. And that's equal to what?
That's 17,576.
That's right, 17,576. Okay?
That's the answer.
That's your answer. Okay? Again, guys, it's just fundamental counting principle. Okay? Remember, you also saw fundamental counting principle if you were looking at a restaurant and how many different ice cream cones could you get if I'm choosing between a sugar cone and a waffle cone. I have 39 flavors and maybe I get a cherry on top or not. Do you know what I'm saying?
Yeah.
I would take all those possibilities individually and multiply them together, and that gives me a total number. 11 says a coin is tossed 10 times. How many different ways can the result be 3 heads and 7 tails?
How many different ways can this be? I don't know. Really? It can only be 3 heads and 7 tails once.
Well, no, you're tossing the coin 10 times.
Yeah, that's how many ways can the result be 3 heads and 7 tails?
Yeah, but that 3 heads could occur on the first 3 tosses, the last 3 tosses, or some other weird combination.
So you do 3 combinations of
Not quite.
3 combinations. You do count principle again?
No, think about it in simple terms. Let's say I'm tossing 3 coins, okay? If I'm tossing 3 coins, then the first one could be heads, and tails, right? But how would you say this? 3 heads and 7 tails. So would you say 2 heads there is the same?
Three heads isn't the same because you don't have 3 heads. You have heads, tails.
Okay.
Oh, but you're trying to reduce it.
But am I going to do a combination or what?
Combination order doesn't matter.
Because order doesn't matter. Okay. So if I have heads, tails, heads, that's still the same thing as this, right? If I do tails, heads, is that still the same thing as that? Okay. So let's say I do a combination of what?
What would you put? I guess 3 because you're going to have 3 heads. Or 3 or 7. Or 10.
Well, see, that's the hard part. How many times am I tossing?
10.
10. So what goes here?
This is going to be 3 or 7.
It's going to be 3 or 7. Does it matter what it is?
It doesn't matter.
I think it's going to end up being the same thing. Okay? Because there's a symmetry on this result. Okay? Do you guys remember doing the Pascal's triangle? And we said that could be written with combinations? It's because they have a symmetry about them. I'm pretty sure this is going to be the same as...
We never did Pascal's triangle. We just watched the video on it.
Yeah, we watched the video. But you saw this as far as writing that in terms of combinations. And you know the coefficients were symmetrical, right? The first and last were the same. The second and second to the last were the same. So if we look at this on the calculator, I think you're going to see that these are exactly the same. Okay? So we're going to do 10, math, left arrow, 3. Okay? Can y'all see that? And we're going to put a 3 here and hit enter. That's 120. And then if I do second entry, I just pull that back up and change that last number to a 7 and hit enter. I get 120. Okay? And I think you'll see that if you look at the formula for this, that is n factorial over r factorial times n minus r factorial. Do you see that? So if n is 10 and r is 3, then I get a 3 factorial, 7 factorial on the bottom. If r is 7, then I get a 7 factorial, 3 factorial on the bottom, which is the same as 3 factorial, 7 factorial. So that's why these two are exactly the same value. Okay? So you're going to get 120 here. Okay? All right. All right. And guys, please think through that. If it's a big problem like 10, think about it in terms of a simpler problem and at least try and identify, am I doing a combination or permutation or what? Or is it a distinguishable permutation? Do you see what I'm saying? Take a simpler problem and think through it and then apply it to the larger problem. Okay? Number 13. Let's see what that one is. It says a group of friends have reserved a tennis court. They find that there are 10 different ways in which 2 of them can play a singles game on this court. How many friends are in this group?
You do permutational.
Don't you play tennis? Who in here plays tennis? Does anybody? Okay.
We do singles games. That means there's 2 of them, and then they have 2 different.
Yeah, there's 2 people. Does it matter that the order of the people is still the same 2 people on the court, right?
That would be 2 combinations. 10.
Okay, so it is a combination. But how many objects am I choosing from?
10.
That's the unknown, right?
It says 10 different.
It says how many friends are in this group. So that's really our X. Okay. Over here, how many people are on the court? 2. And there's 10 different ways in which 2 of them can play a singles game on this court. So that's 10 is our answer. So guys, you can either come up here and plug that into the formula, okay? Or I can just easily try some stuff on the calculator, right? I can do 3 choose 2, 4 choose 2, 5 choose 2 on the calculator until I get 10, okay?
It's 5 if you did this one earlier.
Yeah, it's 5. Thank you. So X is equal to 5.
We did on problem 4.
Yeah, where is that?
3A.
Do you see right here? On number 3A, we did 5 choose 2 is equal to 10. So just using that result, I can solve that problem. Okay? Guys, what he just did there, what Justin did, is a test-taking strategy. If I have a result on a previous question, or even a piece of information, I can use that on another question. It could be one question on the test clues you in on another question. You're like, oh, I don't know how to do that. But then you read another question, you're like, oh yeah, now I remember that question. Okay? So you can't think of test questions independently of each other. You know, some of them may jar your memory for a previous problem. Okay? So again, just always pay attention to what you're doing and think about, hey, does this remind me of anything else I've seen on the test that I didn't know how to do? Okay? Because very likely it will. Number 15. 15. We're at 918 right now. This is in Morse code. Each letter is represented by, why is that sitting there? It's represented by a sequence of dots and dashes with repetition allowed. How many letters can be represented using Morse code if 3 or fewer symbols are used?
You got 26
Okay.
3, so it's 29 possibilities, right?
Do what?
I mean, you have 3 symbols and 26 letters, so it would be 29. 3 or fewer symbols.
Yeah, but it's not 29. Are y'all listening? Listen, you have to read this question very carefully. It says each letter is represented by a sequence of dots and dashes. How many options is that? 2.
So it would be 30.
So that's how many are possible on each spot. With repetition allowed, so every spot has 2. But it says how many letters can be represented using Morse code if 3 or fewer. So I'm doing the problem of 3 plus if I only had 2 plus if I only had 1. Okay? That's how many total are possible. Okay? 3 or fewer. Okay? Every spot here could be a dot or a dash. So we're going to use the fundamental counting principle. So 2, 2, and 2. And those get multiplied. Here I have 2 and 2. And here I have 2.
2 cubes 8.
So that's 8 plus 4 plus 2. And you end up with 14 possibilities. Now guys, I was surprised at that because I'm like, well, how then do we represent our alphabet?
Yes,
Do you know what I'm saying? So I'd have to go back and look at Morse code and see how do they do that with dots and dashes if there's only 14 possibilities? We have 26 letters in the alphabet. Do you see what I'm saying?
That's what I was saying, like, you 23.
And I know SOS is what? Yeah. SOS, if y'all ever need it. Dash, dot. Okay? So if you ever are in an emergency situation, it's dash, dot. So beep, 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 beep. That's SOS. That's an emergency. Okay? I know y'all are grinning, but that might save your life one day. You know? But everyone should know SOS. Okay? But the question is, again, how do you represent all the letters? I'd have to look up Morse code. And we don't have time to do that right now, but I'm going to look it up later. Because when I worked through these yesterday, I was like, how does that happen with Morse code? I don't understand. So, anyways, number 17. Let's scroll down. Oh, that is weird right there. Did it just do a, what did it do? It's almost...
Are you talking how the pages messed up like that?
Yeah, do you see this to
It
this?
does that all the time when you copy it like that.
That's weird. That's weird. Okay, guys, this one is a little bit tricky. It says given 16 subjects from which to choose. In how many ways can a student select fields of study as follows? A major and a minor.
Two combinations.
Order matters on this because one's a major and one's a minor.
Two permutations, 16, or 16 permutation 2.
So 16 permutation 2, which is what? If you calculate that, it's 240. Okay? And I'm sorry I keep forgetting to switch back, guys. But that's a permutation of 16 objects, taking 2 at a time. That's 240. Again, order matters if I have a major and a minor. Okay? B, a major, a first minor, and a second minor. Does order matter?
Yeah, but you have 3 now.
So now we have 3, so it's a permutation of 16 objects, taking 3 at a time. That's 3,360.
It goes up that much with one.
Yes, it sure does. Which is pretty amazing. And then the last choice is a major and 2 minors.
Which is what we just did.
How do we do that?
Same way, 17. I mean, yeah, 16 per day and 3. Same answer. It's still going to be 3 classes.
Well, can I do fundamental counting principle?
I mean, why can't you do it with permutation?
Well, we will, but we're going to combine it. How many options do I have for my major? How many possibilities for the major?
16.
Okay, so 16. And how many for 2 minors?
16.
If there are 2 minors, does order matter? No. So what am I going to do? Combination of what? How many subjects do I have to choose from
16.
if I've already picked one of them for my major? So now it's 15. And I'm taking 2 minors, so 2 at a time, and I multiply these together. You actually end up with 16 times 105. Your combination of 15 items taken 2 at a time is 105. Times 16 is going to be 1,680. Okay? And then you're done. Alright? So again, that's a weird one because you actually combine your fundamental counting principle with a combination. Okay? And why do you do that, guys? Because combinations and permutations are simply a way of counting up possibilities. It is a means of counting. That's all it is. I don't know. I can't remember what I asked on the test. I mean, off the top of my head. But I think if you understand what you're doing on these, you'll do fine on the test. Okay. But again, be aware that when you're trying to count something up, ask yourself, can I use a combination? Can I use a permutation? If I'm counting these possibilities, can I do that with a fundamental counting principle where this choice and that choice are independent of each other, or somewhat independent? And yes, you can. Because once I've chosen my major, what I choose for my minor is not dependent on that. I just knock down the number of choices to 15. Okay? And then that makes those two independent of each other. Okay? All right. Guys, listen, it is 9:25. Which one are we on now? God, I scrolled down and I should be over here. Back up here. Yeah, 19. Guys, how about we wrap this up? Okay? And are y'all listening? Listen, my other classes, like my next class in particular, are y'all listening? Listen, we'll finish out 19 through 39, and I will post that online. Okay? Now, if you need to before the end of the day, download it. Okay? But I'm going to post what we did in class today, and I will post what I do in my next class, and you will have all 1 through 39 problems, except for maybe number 39, because personally, I still can't quite wrap my head around that one. I'll look at it again today, but I'm not sure I understood what they were doing on that one, so I got to look at that one again. But the rest of them will certainly be posted online, and you'll be able to look at those tonight before your test. Okay? And make sure you review your binomial probability, because that will be on your test as well. Okay? So we will pick up next period at number 19 and go from there. Hold on.